Concepts of the rank and the shape of a tensor are both really important ones. So here is a question that I'd like you to keep in mind as we process this video. The rank of a tensor is an integer. For instance, a scalar has rank 0 and so on. The shape of a tensor is what? What, for instance, is the data type of the shape of a scalar, or for that matter, the data type of the shape of a vector? While discussing computation graphs in TensorFlow, it's important for us to understand the distinction between building a graph and running a graph. These are two distinct steps in any TensorFlow program, and it's important for us to realize what's going on in each of these. As the name would suggest, the process of building a graph is all about defining the computation graph, specifying the operations and the data, in a sense, defining the edges and the vertices which constitute that graph. But as with other tools where transformations are modeled using DAGs, the step of actually running a graph is separate. This involves actually executing the graph to get a final output. This idea of a sharp distinction between building a data representation and executing that data representation is once again not new or unique to TensorFlow. Consider, for instance, how RDDs are evaluated in Spark. RDDs, or resilient distributed datasets, know their lineage. They know the exact set of transformations which resulted in that particular RDD coming into being. And so RDDs are lazily evaluated and only as a result of an action and not as the result of a transformation. In any case, let's now double click a little bit and understand in detail what building a graph and running a graph entail. As an aside, you should be aware that Tensor Board, which is a great visualization facility available in TensorFlow, helps with both of these parts of the computation process. Both the shape of the computation graph and the intermediate and final results, both of these can be viewed in TensorBoard. We'll check out TensorBoard when we get to the demos. Let's now turn our attention to lazy evaluation and the distributed nature of computation graphs. To understand how this is possible, let's zoom in on a couple of nodes. Virtually any node in a directed acyclic graph can be thought of as the output node of a smaller directed acyclic graph. That smaller directed acyclic graph consists of all of the dependencies of that output node. Now, given two different unrelated nodes in the larger DAG, each of these can be evaluated separately. Clearly, there is no intersection between the dependencies of these two nodes. And this serves as an indication to us that the computation of these two smaller subgraphs can be parallelized. Another implication of this is that there is no need to calculate the entire DAG simply for this one output result. TensorFlow can easily figure out and calculate only that portion of a DAG which is required for the evaluation of a particular node. Exactly as in other data flow technologies like Spark or data flow on the Google Cloud platform, lazy evaluation and distributed processing go hand in hand. As soon as one is able to create logically distinct subunits of our original DAG, these can then be evaluated in a lazy manner, and what's more, that evaluation can be distributed. It can be performed in parallel across machines in a cluster. So keep in mind both of these aspects of TensorFlow's performance. It relies on lazy evaluation to only evaluate that subpart of a directed computational graph which is required for a particular output. And in addition, it will distribute the calculation of the computation graph over many machines in a cluster. Let's now double click on the term tensor. Clearly, tensors are extremely important in TensorFlow. That's why TensorFlow has gotten its name. Let's understand what they are. Tensors are the edges in our computation graph. They connect the nodes which represent different data transformations. At heart, tensors are just data items. Let's look up the docs. The docs tell us that a tensor is a central unit of data in TensorFlow. Indeed, all data items in TensorFlow are tensors, and tensors form the edges of the computation graph. Now, a tensor consists of a set of primitive values shaped into an array of any number of dimensions. Let's parse this. Every word here is important. The primitive values could be ints or floats or any other basic types, i.e., not containers. These primitive types have been collected into some container, which is an array, and that array could have any number of dimensions and any shape. Let's understand all of the properties of tensors Scalars can be thought of as zero dimensional tensors. So, for instance, the integer 3, the double 6.7, the single character a, each of these represent zero dimensional tensors, which are scalars. We can extend this to vectors. Vectors are one dimensional tensors. These are defined by one square bracket on each end. This is important. Vectors are defined by one pair of square brackets, that is, by one square bracket at each end. Let's extend this. We can increase the number of dimensions. For instance, a matrix can be thought of as a two-dimensional tensor. This has rows and columns. In order to define a matrix, you would use two square brackets at either end. So matrices are two-dimensional tensors which are defined by two pairs of square brackets. And generalizing, the number of dimensions is equal to the number of pairs of square brackets. So for n dimensional matrices, these are n dimensional tensors and they will require n pairs of square brackets to open and close the tensor's dataset respectively. So tensors have defining characteristics. In fact, they have three defining characteristics. These are the rank, which is the number of dimensions in a tensor, the shape, which is the number of elements along each dimension, and lastly, the data type. This represents the type of each element in the tensor. The type is pretty simple, but let's understand the rank a little more clearly. We've seen this already, that the rank of a tensor can be thought of as the number of square brackets that you would use while defining that tensor. So scalars are tensors of rank 0, vectors are tensors of rank 1, matrices are tensors of rank 2, and tensors which have a rank higher than 2 are just called n-dimensional. The shape is a property of a tensor which tells us how many elements exist along each dimension. Now, in reality, there can be a couple of types of shapes: the static and the dynamic shape, which correspond to the maximum possible number of elements in each dimension, and the current number of elements in each dimension, respectively. It's also important to note that the shape itself is a vector. It's going to have one element corresponding to each dimension in the tensor. So, for instance, the shape vector of a scalar is the empty vector, that's just a pair of square brackets. The shape vector of a vector is going to consist of just one element, that is the number of elements in the vector. The shape vector of a matrix is going to consist of two elements, that is the number of elements along each dimension of the two-dimensional matrix. And for an n-dimensional tensor, the shape vector will have n elements. That's as far as the shape goes. The last defining characteristic is the data type. The data types of tensors are pretty familiar: ints, floats, strings, booleans, all of the usual suspects. So do keep in mind that every tensor is a multi-dimensional set of primitive values. Every tensor has three defining characteristics, which are the rank, the shape, and the data type. Let's come back to the question we posed at the start of the video. The rank of a tensor is an integer. This is something we saw. The shape of a tensor is a vector. This also is something that we saw. For instance, consider a scalar. A scalar has a rank 0. Now, the shape vector of a scalar is going to be an empty list or an empty vector. Consider a two-dimensional matrix. There the rank is 2. The shape vector has two numbers within a list because the shape vector tells us how many elements are present in each dimension. So again, the shape of a tensor is represented by a vector.